Welcome, everyone. This is actually our first Spark Dialogue of the Year, this UW Space Policy and Research Center. I am happy to introduce Professor Missy Cummings. She is currently a faculty member, but on leave from Duke University. She is working for the Biden administration as a senior safety advisor right now for the National Highway Traffic Safety Administration. Her background is in autonomy, human factors, safety for a range of autonomous systems. So the highway is just part of it. What she does in terms of technology and policy applies to pretty much any domain. And we thought it would be good to have her come in and talk about what's going on in her part of the world and how that may relate to space. So Missy, I'm going to turn it over to you.
All right. Thanks for that great introduction. I'm a longtime friend of the department, an adjunct professor, depending on the year. I haven't been able to come out much this past year because I've been working for the Biden administration, primarily helping them develop policy around autonomous vehicles. That's both self-driving cars and cars with driving assist. And I can't really go into detail about what I'm doing for them. It's kind of the deal I made with them, is that, you know, I can't be a spokesmodel yet, although I'm done in about 4 weeks. And so in about 5 weeks, I'm going to be very sassy and blabby. And then, but also as part of that, of my current position, I'm actually not allowed to give any presentations with any PowerPoint slides at all. Because they have to go through some kind of clearance, and even if it has nothing to do with driving, they just don't want me giving out any slides. But what I can do, what I am allowed to do, is to talk from published papers that are in the public domain, which is kind of a back door. So what we're going to do is we're going to go revisit a paper I did. we're not going to look at words. We're only going to look at pictures. I don't want to bore everyone, but we're going to go back and we're going to go back. I'm going to take you on a joyride of 17 years ago when I did some research for Draper Lab, and this was part of the Big Lunar Lander program. And what's weird is when I went back, when I was getting ready for this talk, I went back and, you know, the other professors in the room would be with me. Did you ever go back and you read a paper and you were like, damn, I was good back then. That was a good paper. Like, who was I back then, right? And what's crazy is that this paper is probably even more relevant today than it was 17 years ago, which is a little depressing because it has been 17 years, and this paper was when I was a professor at MIT. However, it also, while it might be a little depressing that it's still relevant 17 years later, it just kind of will illustrate to you the power of really good research and really being able to look forward into a crystal ball and say, these issues are going to become important. And it's really one of these, a testament to, if you really believe in something and you know something is important, stick with it, because I'll talk to you today about how this 17-year-old paper was relevant then, it's relevant now, and it's not only just relevant to space, it's relevant to many other domains, as Christy referenced. All right, so let me pull this up and I'm going to share this paper. Now, I'm only going to talk about 20 minutes and then we can go to questions. And then when we go to questions, we can talk about anything. We can talk about the space applications here, or we can talk about, you know, how these apply to other domains. All right, so this was what it was. So back in 2005, there was a lot of research going on to look at, we were developing, the country, NASA, wanted to think about going back to the moon. That's actually why it's so crazy. I'm like, I totally forgot about this. I'm like, oh yeah, that's right. 2005, we were going to go back to the moon. And then there was all this research activity. I'm sure UW was part of that as well. And then I guess we decided there was not enough money. You know, it's funny, maybe other people on the call can help refresh my memory. Like, I'm not sure why it went away, but then it went away for, you know, to look at other research. You know, then we decided to put sun orbiters and other vehicles up in space. And then, of course, now that the Chinese have been to the moon, ooh, we got to get back to the moon, right? So this is part of that sine wave that of what is research. So now it's come back into fashion. So at that time, I was a relatively new baby professor at MIT. And this is the team of my team, bunch of students on it. And this was when I was running the Humans and Automation Lab. Okay, so it's a very long, it's actually 121 pages. I couldn't, you know, but the first thing I want to talk about is, okay, so we were tasked with, we need to figure out how to design a new lunar lander module. I mean, I was on the team. It was led by Draper, and I was just one of many minions, professors on the Draper team. And so my part of the project was to design the decision support system for astronauts inside the lunar lander. So if we go back to the Apollo era, you know, this is them trying to find a landing spot on the moon and trying to figure out where to set it down on the moon. Okay, so, you know, now it's obviously 60 plus years later, we're just going to figure out a better way to do this. So how can we do that? So the first thing I did, and by the way, when I saw, I'm like, I should use this more often. I had to find a way to describe if you're going to design a system that includes both humans having to make decisions and autonomous technology, computer support to help the humans make this decision, how does one even, where do you even begin, right? So we begin by mapping, this is like a domain map. So what you see is they're really, I'm not sure if it's showing up very well, but you've got 3 circles. You've got operators. These are the astronauts inside of the lunar lander. You've got technologies that they're going to use. And then you've got the task, because there are going to be restrictions, constraints, goals that are going on for these tasks that may change what the technologies need to be leveraged, and maybe even who the operators are. So first you have to define the operators, the tasks, and the technologies. And then what you do is the arrows that point between them are showing you the analytic processes that must happen so you can get a sense of, okay, what is the requirement space that I'm dealing with? So all of this analysis that I'm going to talk about up front is, we just needed to get a sense of what are the requirements for the technologies and for the people. So we find out what these requirements are. And indeed, these were going to be the deliverables that went to Draper that then would go into some larger contracting process that would then, or should have led in like 2006 to a lot more money and building up the space program, but it didn't happen. So the first thing is the cognitive task analysis. And a cognitive task analysis is when you basically find out what the cognitive needs are someone who's doing a primarily intellectual task. I say that because the astronauts are just sitting there. There's not a lot of physical output. It's not that there's not physical stressors on them, but for the most part, they are doing a task that is completely within their brain. So you can do a regular task analysis if you want to do, you know, like, are people doing a lot of physical work, for example? So if I wanted to develop a decision support system for construction workers, I would actually need to go with them. But this was in the field, but this was really primarily cognitive. So to do the cognitive task analysis, we actually went and interviewed a bunch of astronauts. And if you want to read this document after I'm done, after I've showed it to you, I will send it to you, because we interviewed Buzz Aldrin and some other astronauts. And so, God, it was such a fun time. I totally forgot about this. That's right. Oh, that's right. Buzz and I were hanging out back then, and before he was a little crazy. And so it was it was just really great to sit down with an actual astronaut, and he wasn't the only one. There were a couple more that are in this analysis, and have them tell you what were they thinking, what were their processes, and it's all detailed here, so you can read about what he was telling us. So once we got done interviewing the way it was done, then we went over to do a sensor survey. And the sensor survey was, look, the technology that was available in the 1960s is very different than, and now it's been 60 years, but it was 40 something years back then. But 45 years later, it was, we had different technologies. And the question was, how are the new technologies that we have available potentially going to change the task? Now, this is when I hit the first third rail of astronaut control freakism, which, for those of you who don't know, I was a former fighter pilot. So it's funny to me that I was shocked, I'll tell you, by how much control that the astronauts wanted over this task, because I'm a control freak, so I should have totally been able to anticipate this. But this kind of manifested in the argument about, does the lunar lander need windows? Oh my God, I cannot even tell you the knockdown, drag out fights that we had. Engineers at Draper, professors and teams of students at MIT, the astronauts, both recent astronauts and much older astronauts like Buzz Aldrin. The astronauts and NASA as a whole were very pro-window. They all wanted a window. And this was kind of like the hill that they were ready to die on. We were going to have that, they're going to have that window if it kills them. And I'll explain why a little bit later when I show you some pictures. But we were looking at, look, windows are a huge engineering challenge, especially in the vacuum of space. So wouldn't it be great if we could get rid of that window, which actually doesn't give you the greatest visibility? Wouldn't it be great if we could replace it with cameras, so that the cameras could give you much better views than you could out of a window? It's funny because nothing was ever built, so I don't know where we would have ended up at the end of this death battle, but I'll be interested to watch it with the new push for lunar landers. But it's really, it's a good explanation of, like, or a good example of when people feel passionate about things, and I'm sure all the older professors on the call are going to get this, like, you can know the best solution. You can have reliabilities of whatever, and you think you can do that. But sometimes we make choices because of cultural reasons. Even in very technical systems, we will often make choices based on culture, not necessarily on clear and obvious science. Okay, so that was a big part of it. And then kind of the last piece of the requirements puzzle was doing some human in the loop testing. Now, I mean, we're still talking about a futuristic system that wasn't designed, but by testing, we mean, okay, we have some design concepts and we want to do at least some preliminary human in the loop testing to get an idea, is what we're proposing, is it going to be usable? Is it going to reduce people's workload? Is it going to actually meet the mission performance requirements? Okay, now, in the middle of this, what you see is this function allocation. And this is really the heartbeat of everything. When I do human interaction with autonomous systems, that's my work every day. And understanding that balance, the teeter-totter between, do we have exactly even roles between humans and automation that's completely balanced, or do we let the automation have more functionality, or do we let humans have more functionality? And that's, I've written several papers about how do you know when to make that balance, right? And often, because of some of these cultural inputs, sometimes, again, it becomes suboptimal of what you think is the most efficient way to design a system, but it is what it is, right? I mean, you have ultimately NASA is a customer, and so you'll go with what the customer decides. So it's this complicated balance of having to do all three of these to kind of come up with what we think was happening. Now, so we did that. I love this picture, by the way, because it's political correctness. I hope you can see it. I'm kind of enlarging it. gang, you can't get this anymore. If for no other reason, you should ask me for this paper, because after I published this, Draper got rid of these pictures. That's because it was just so phenomenal for me to find out sometime in the 1950s, this is the early 60s, they actually were wondering, I wasn't even born yet, and NASA was having this argument about function allocation. Do we let the astronauts all just sit there and have the whole system be automated and all the astronauts do is have an abort button? Or should we have the astronauts fully engaged in all the tasks in the lunar lander and have them extremely busy? So, and it was funny because, and the reason that I brought this up in 2005 is because it had been 40 years and we still haven't gotten to a right answer. Now we're in 2022 and it's still relevant. Like, we still can't come to an answer. And I guess that's a good news, because if we were able to easily come to an answer now, then maybe I wouldn't really have a job and my services would not be needed. But here we are, my services are still needed. What's so great about this cartoon is these are the original cartoons. They're coming out of the MIT Instrumentation Laboratory, which then eventually became the spin out of Draper. But you can see here that the three astronauts, one is smoking a cigar. So I published this paper, and then later I went back to Draper to get these pictures again, because I wanted to publish a new article that didn't really have anything to do with space, but I was just trying to show the history of how long this has been an issue. The pictures they gave me 5 years later in 2010, they had photoshopped the cigar out off this guy. And now he just looks like he's sleeping. Oh my goodness, that's so funny. It's just funny to me that you know, look, I don't know, maybe Mad Men hadn't come in yet as a TV show. Look, people were smoking in the 60s, right? You don't have to be that politically correct. But still, if you want the original pictures, call me, because I've got them. Okay, so it's a long-standing problem. We're not really sure how to do this. Indeed, this is a picture from the 1960s lunar lander. This is the kind of dials and gauges. Hang on. This is exactly the time that the sun has decided here. The sun is setting. A bit better. Okay. And let me know if you guys can't see anything. So dials and gauges. You know, what's funny to me is when I first saw this picture, I thought, that's a picture of a submarine. You need to show me the lunar lander. And it was the lunar lander. So it's like the engineers for submarines, not surprisingly, probably all just kind of marched over and helped design the lunar lander because they look the same. I mean, you know, back in the day, that was the way designs were, but you can see that, you know, workload would be high. It wasn't obvious necessarily what was going on. Certainly not to the degree that we have digital displays and things like aircraft now. All right, so understanding what was in history, what we were up against, we actually came up with a prototype. And so the prototype of what it was going to take to support, and at this point we were saying, you know, there's a mission commander and then the lunar module pilot. So there's two people sitting at this console with a wraparound of 3 displays. And it actually, until just a couple of years ago, Draper used these pictures from this report as, like, you know, they're showing their cutting edge. I don't know if they're going to bring it back. I should ask them, like, you know, are you guys going to bring up this research again? So notionally, it was for 2 people, but it really could be handled by just 1 person. And not even that 1 person necessarily has to be in the lunar module. So that was another big debate that we had in this. So do humans really need to be here at all? I mean, you don't need a human to, you know, depends on the mission, right? Should you keep them on the Do you need to have somebody actually going down to the moon's surface? You know, and again, it's funny. It's almost like, don't raise it, because depending on who, you might piss somebody off and they'll be very angry that you even insinuated that a human doesn't belong there. So, you know, I was really taken aback at the time, but now that I'm much older and wiser, I get that a lot of the reasons that humans fight automation is because we want to believe that we're still relevant. And it's kind of like a John Henry, if you've ever heard the parable about John Henry building the railroad. And there is some of that in us, right? We want to believe that we are so critical to any problem that we can't be automated out. I do think with the rise in AI, especially in driving, and I see this every day. We are not going to be automated out anytime soon. If you think you're getting a self-driving car anytime soon, I would not bet on it, right? Probably, even in my own lifetime, it's going to be, we're only going to make incremental progress in this space. So I think that there's the complexity of some jobs are such that we're going to have nice job security for a long time. But even things like remote lunar landing, I think we need to realize it's not a replacement, it's a collaboration. And I'll come back to that because I think that that is a real common misconception about when you start to automate elements of any complex task, this function allocation, push and pull, you need to come back to it saying it's not either just sitting around smoking, waiting for something to happen, or running around like you're a chicken with your head cut off. These two ends are hardly ever the reality. The reality is that, sometimes you need to come in some more often than you thought you might, or, maybe the system wasn't as busy as you thought it might be in some other environments, but it's really going to be dynamic and you're going to need to adapt. Okay, so let me just quickly go through what these three displays were. The first was the landing zone display. So this is a picture of, remember I told you that Buzz and those guys just really wanted to have a window. And this is their heads-up display for their window in the actual lunar lander. They had some etchings on the wind screen, if you will. And when they were landing, they were basically, it's not quite as bad as drawing a marker on your screen, but at least it was etched in there. But, they had to make sure that the orientation of the lunar lander married up to the etchings on the windshield to make it correct, right? So that alone, just when I thought about that, woo, that's pretty brittle, but they made it work. That being said, that first moon landing, it wasn't as smooth as you would have thought it would, thinking historically. And you can go read back through this report to find out kind of what the problems were. So and this is where now you're seeing why the camera was such a big deal, because we were proposing that if you could put cameras on the outside, you could get a much better visualization of the moon surface than looking out of the corner of that little windscreen. And you could actually get a lot more information to allow the astronauts or the lunar module pilot, as he was coming down, he or she would have a lot more clear information. And so what you're basically seeing is how we were envisioning kind of a new heads-up display for pilots coming to land on the surface of the moon. There's some information. This is a tape display, very similar to what you might see in a cockpit today. Information about fuel. And what this circle here is that this is now harnessing the automation to plan an optimal landing site. So you can imagine you're kind of coming at the landing site like this, and we'll do some more pictures. You got some velocity vector information here. And this was a new landing aid that eventually I got a patent on, because the idea is this thing, it's called the VAVI, the vertical, it helps you with your vertical descent. We'll see that. I'll show you a little more pictures, but it basically helps give you an idea of how quickly you're coming down, as well as exactly where you are above the ground. And then this little picture here was if we had better sensors, some kind of millimeter wave radar, for example, that could map the landing site in front of you, it could help tell you where elevation points, for example, were just too high for what it is that you were trying to do, and you would need to steer away from those. Okay, so this is the VAVI, kind of like, now you can see as you're starting to come close to the ground, the VAVI was like one tall, thin rectangle. And then as you started to come down close to the ground, the arms would start to come out. and the movement of the arms, and you can read about the cognitive science when you go into the report, but it actually helps you understand your rate of descent and how well you're to control your touchdown, or how well the computer is controlling the touchdown. And so eventually though, if you actually go read my paper on the VAVI, what you'll find out is in the final design, one of the arms dropped out because we decided really only pilots really needed just half of that display. So even at this point in time, there was still early thinking. All right, so I'm sorry, this was the fuel and thrust gauge. Well, now we really look like we're playing a video game for a pilot, but you know, the pilots, they don't really need this, but they really wanted this. And so, you know, your roll indicator to find out how much roll that you had on the vehicle, you know, standard pilot instruments. It's interesting. It's like a security blanket. Oh, really love it. You know, I feel really comfortable when I have my roll pitch yaw indicator. Even though you can get that information from other, you know, probably more clearly in other ways, we still really like it. And, you know, pilots really are the culture of people that we're pulling from. Okay, so now these are just like, okay, oh, we're coming up closer on that landing site, coming up closer on the landing site. Now you're basically on top of the landing site and your view transitions because now you're just basically going to do a complete vertical descent down. All right, and that's kind of like blah, blah, blah. All right, moving on, that's enough. You could redesignate and kind of move your display over. It's pretty cool. We'll see what really comes out in the final, if any of these ideas make it to the new lunar lander. Now, the next display that we had is something we call the situation awareness display. The idea is that, you know, with all this computer technology, pilots did not, and astronauts did not have to guess where they were in the profile to landing, right? Because you could plot it out. So in this case, you know, you would descend here, there's some critical thresholds in the green, and then you would get to this point and then do a complete vertical landing. So, you know, you could tell at any point in time where you were on this planned trajectory. And this isn't fighter pilot world where you're doing any rocking and rolling. There's really going to be no uncertainty, hopefully, in terms of at least where you are in your profile. There is some uncertainty around the landing sites, and that's because, well, for example, millimeter wave radars, I mean, it's pretty good, but it's not perfect, right? And indeed, that's kind of why you do need a human there at the last minute, because some of these sensors, while they're great, they're not perfect. And so you do need a human to eyeball some of the issues, although that human doesn't necessarily need to be in the lunar lander to do it. And on the situation awareness display, we were able to give a checklist, and you know, it's very clear where you were in the checklist. You were in the braking phase, the free fall phase, the terminal descent phase. So it would be very clear. By the way, they did not have any of this in the 1960s. They had checklists, but they had to envision all of this in their head. It was just like, I think I'm here. And they were listening to mission control, right? So mission control was an absolute necessity. I mean, and it still is. We rely way too much on mission control. And of course, I'm going to say that as a person who does mission control design, but the reality is, if we're ever going to do long space duration flights, we're not going to be able to be reliant on mission control. So I'm a big fan of trying to break away from mission control as the know-all, end-all, be-all control authority in space missions. Okay, so profile view, we'll just zoom over that. And get to the last display. Yeah, it's like 121 pages. I tell you, it took me forever to get through it. Okay, last but not least, we had like a health and status monitoring page. And so this was really important because, you know, you have a lot of systems, subsystems, and indeed, so what this page was doing, it would allow you to select, I forget what LSS stands for, but this is the lunar module. This is the lunar life support system. So life support, so this is basically what's keeping all the humans, keeping you alive, and this was basically what's keeping the module together. All the subsystems, master caution, we had some, you know, fuel again, you know, just information that people would need at any given time. Okay, let's see, anything else interesting here? No. Okay, so then we actually we presented this. I'm going to see if I can come back to some better pictures. we presented this to, after we had talked to all those astronauts, we went back to them and we said, well, what do you think about this? We had a few human in the loop studies to say, you know, and here, what you're actually going to go back, you'll see where we took some designs from aviation, other aircraft, and we said to them, and I'm just going to leave it here. And, you know, we try to get their feedback and we made some design changes. Indeed, that's why when I told you about the VAVI, that did this dual arm thing, because of those human in the loop trials, we actually wiped off one of the arms because we recognized you really only needed one. So it was a great project. We had, you know, it was so fun as a young professor for me to be able to get in there and meet and talk with all these astronauts and really study this in depth. Be a part of a big team working on a big important project. And then of course, a year later, after we submitted this report, the project was canned. All the other professors on the call will actually say, that's just the cost of doing business, right? You were in a very important project and it was fun. And, you know, all this great intellectual work came out of it. And then Congress decided to do something else, or, you know, that there's just forces out there that you can't control. And I forgot about this paper because, you know, it was canceled. I moved on to other things. It's funny, I think about where I could have gone, because I was doing this project at a really critical juncture in my career where I was doing, you know, a lot of aviation. But I mean, I spent a year fully immersed in space. And had that project gone on, I think I would have continued more and been more of a space person. But because the funding got cut and then I had to adapt and get to other projects, I actually then rolled over into unmanned aerial vehicles. So that was my trajectory. And then my whole career, you know, I got tenure at MIT because of my work in UAVs. I got famous, at least on the Comedy Channel, you know, appearing on, you know, The Daily Show and Stephen Colbert Report. And, you know, then my career just kind of took off because I went into UAVs. And, you know, and eventually that kind of propelled me to get over into driverless cars. And so it's just interesting when I was taking this historical look at my own life, I was like, oh, wow, you know, I wonder if this country had set itself on the path of really going back to the moon in 2005, I would be a different person talking to you today, but we didn't. And here I am 17 years later, after I wrote that report, everything in every word of that report is still very relevant today. I actually thought about, look, I'm just going to send this thing. I'm just going to send it back again to everyone. I'm not even going to change anything and say, look here, you guys need some lunar lander planning. There's, you know, hundreds of thousands of dollars of work that went into this report. So here, have at it. And we'll see. It'll probably get canned again. And, you know, we'll go back to the moon. The next time we go back to the moon, I'll probably be dead. But it is a good reminder that your research will become valuable again, even if you don't think it's valuable right now, or, you know, there's some kind of ebb and flow of time and what was popular is not popular. If you just live long enough, it'll become popular again. Okay, with that, why don't we take questions?
Awesome. Thank you, Missy. I have lots of my own, but I'm going to go with the ones that are in the chat here to start. So first one from Prussia, understanding automation is still on a far horizon. Is there federal legislation considered, if you can say, to prevent the state level decisions, creating confusion for OEMS operators who wish to roll out national autonomy AV UAV programs? And again, I know you're limited by what you can say right now. I mean, in 5 weeks, it might be a different answer.
Yeah, no, I mean, I can talk to this question because it's kind of a bigger issue. So OEMs are original equipment manufacturers, for people who don't know. So the question is, who should be making the decisions about technology? Should there be federal regulation or should there be state regulations? So for example, if you want to have a drone port at UW, you guys, and let's say you've got some great professors there and you guys are building flying air taxis and you want to test them, and So who should give the approval? Should it be Dub? Should it be Seattle? Should it be the state of Washington? Should it be the federal government? Indeed, the reality is all of those organizations get some kind of vote. But ultimately, for aviation, the FAA has said, we own the airspace. The inch above, like the instant your foot leaves the ground, we leave the airspace that you're in. And so we have a very strong regulatory authority in terms of aviation, who has basically kind of laid down the law, and everybody is expected to fall in line. Now, does that mean that the states still don't have something to say? They will have something to say, particularly when it comes to things like emissions. You know, like flying air taxis aren't going to, you know, if they're electric, you know, this is very pro emissions, but still, you know, states can, there are authorities that states have that are going to be connected to a technology. Some companies don't like that. They either want the federal, what companies want is, first of all, no one to regulate anything. That's what they want. I mean, you know, so to be fair, I mean, of course, that's what companies want. They don't want to be told that they can't do something. But especially in the driving world, companies would prefer one unified strategy for autonomous vehicles as opposed to letting the states make decisions. That becomes a problem because, and this is where, remember that function allocation piece I was telling you about? So the way that our authorities have been, our legal authorities have been set up in this country is at the federal level, NHTSA governs vehicle technologies. So NHTSA is the one that says, if you've got technologies on your car, they have to meet these standards. And if we don't address it in our FMVSS, the Federal Motor Vehicle Standards, then you can do whatever you want. But the states regulate the driver. So that's how come you get your driver's license, and you have to get your eye test, and you pay your tax, right? Because states oversee the human driver, and the federal government oversees the technology. Now, this is where we're in a kind of a conundrum. Well, guess what? Autonomy is both things. Autonomy is both the driver and the technology. And so I have to tell you, like, on any given day, states are going, oh, federal government's like, I don't know, where's the middle ground? Indeed, I've spent a lot of my time at NHTSA trying to be the kind of the middle ground between states and the federal government. And so much so that in 5 weeks, when I'm no longer working with the federal government, I'm still going to be a consultant to the state of California about autonomous technologies, because I'm still going to try to help states kind of, you know, they have an important dog in this fight. And we can have a bigger conversation about that later. But in surface transportation, we have a clear separation, which is causing some conflict. In the aviation world, the federal regulation environment is so strong that they just kind of like the edict, and then the states are kind of there to support kind of the peripheral infrastructure. So it's not the same. And I think probably even the bigger question mark is over the head of the FDA. Oh my God, we're going to start putting autonomy in medical technologies. No, thank you. No, thank you. I'm just going to say, and they'll be so bold and say, I'm not ever getting an operation by a robotic surgeon. I'd have to sit with a surgeon who was going to operate on me, and I'd have to watch him do about 1,000 surgeries before I'd let him operate on me. Oh my God, right? So we're still so far away in the medical domain from even being anywhere near the kind of safety levels that we enjoy in aviation, and even for transportation, surface transportation. So that was a very long answer, but the answer is it really kind of depends on the environment.
Cool, thank you. Okay, next one from Robert Jaeger, or Jaeger. I'm not actually sure how to pronounce that. Sorry, I got it wrong one way or the other, or both. Extremely interesting presentation. Many thanks. Would be interested to know about existence of formalized or documented model or process to decide on function allocation as tech changes, et cetera. Dynamic algorithmic approach to vehicle and system design seems desirable.
Agreed. You know, I mean, you're not going to get pushback. The reality is most AI today, and even automation is so narrowly focused because that's the only way you can get it to perform in any reliable sense. So I am all for adaptability, in any kind of system. But I just think, and this is actually where in academia, we need to work harder to make that a reality, because there's not been a lot of transition. I mean, I think it's funny when you work in academia, you get to spend so much time pie in the sky thinking about the way the world should be. And then I did, a couple years ago, I did a sabbatical with Amazon. And then Amazon robotics, like warehouse robotics. And then you're like, oh, we don't need any fancy algorithms. We just need one algorithm to work all the time. That's really all we need. It just needs to work and not have any problems with reliability. And so it's funny, it's great to go from academia where the sky's the limit when you have to go down to work and you're like, no, I need this thing to work all the time. And my algorithm breaks if there's too much dust in the air, right? So, I still think that we've got, and it's the uncanny valley between academia and the real world. It's still very much in place. And so, this is something that as a baby professor, we talked a lot about it, but it's still a big problem. And for good or for bad, being able to take really great ideas that are coming out of academia and making them work in the real world, I still think there's a huge piece there. And indeed, that's actually why the NSF started their technology innovation program. There's a whole new directorate at NSF, and they did that for the exact reasons I just said.
Yeah, following on that a little bit, because I think this relates into it, many people for many years have looked at this area of what's called variable autonomy. So, much of what you've been talking about so far is the autonomy is fixed. Like there's a certain set of functions that are assigned to autonomy. There's a certain set that are necessarily handled by human operator, and that's not flexible really in the frameworks that you've talked about. But there has been lots of conversation and quite a bit of research into how would you define, first of all, define, and then implement in any way variable autonomy. What's your thinking there?
Yeah, a little bit of that, depending on what aspect of the task you're looking at. There was some variable autonomy in there in terms of when the automation would require an input from the human. So, it's a great idea, but the more variable your autonomy is, it means you need a more specialized human. And I will tell you, one thing is clear in cars. No one ever should have their hands not on the steering wheel. So, and I don't care what manufacturer we're talking about, because you being able to have your hands not on the steering wheel for some period of time, that is variable autonomy, right? You can have, sometimes you're driving, sometimes you want to let the car do the driving. And one of the things that we're seeing for sure is the instant you're taking your hands off, even if you think your eyes are on the road, your brain is not on the road. So for your everyday driver who has received very little training, is not really certified beyond a very easy driving test, variable autonomy, I think, is a nightmare. Now, as a fighter pilot, I got lots of training and had to do annual check rides and yada, 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 right? So there may be some domains where variable autonomy is fitting, but I do think people need to realize that getting the human back in the loop at the right time in the right place can be a disaster.
Yeah, and I think like what you're saying about like when you're a fighter pilot, fighter jets don't fly in the same places. Like they're not in general aviation. They fly in very particular conditions in particular places. And the same thing with space. I mean, even though we're talking about getting lots more humans up into space, it's still not a large N, and they are very, very trained, and the operating conditions are very easily characterized. There's not as much variability in what can happen. It's pretty bad if something goes wrong, but oh, you're muted.
Of course, because my daughter is coming in the door right now and so yes, exactly. Because in some domains where you can control the environment, or you don't have you know, like mining is a good example. I think the mining community can do a lot more and try a lot more and be more experimental because they have complete physical control over the space, and you don't get some random dude driving through the mine site, jumping into his back seat while he's trying to see if the car will drive by itself. You know what I'm saying? So yes, variable autonomy, good at the right time in the right place, but those instances are probably going to be small.
Awesome, thanks. All right, I see Eurus waving his hand there because I knew he was going to have a question, of course. Eurus.
Hey, Missy, it's kind of an interesting one. You want to pop back to, or it's probably not that easy to do, but back to the Venn diagram?
Yeah, I can bring you back there.
And so I have some questions about how, okay, you know, I don't know whether the rest of the audience is familiar with the history of the Venn diagram and how it has influenced thinking in many fields, engineering, social interactions, learning, on and on and on and on. But there's an underlying assumption in here that I think is relevant to what you're talking about today. And that is, notice what the Venn diagram does. I can take the three circles, which denote technologies, tasks, and operators, and that's where the human is in the functional allocation. And the typical use of a Venn diagram is that these circles grow equally. And because what is really critical is that little tiny intersection of the three circles down in the middle. And the history of Venn diagrams and thinking along those lines, whether it's engineering, social science, psychology, whatever, is that you have successfully married operators, technologies, tasks, whatever those labels, or any other labels that you use applied to that Venn diagram. If they all grow, then the objective is to make that little intersection big as possible. And in the perfect world, they all coincide and there's perfect integration. Now, the question that I have is, so obviously this was something that went into the thinking 17 years ago. I think I encountered Venn diagrams 40 years ago. But the problem is, what happens if technologies, which is what we're talking about today with automation, that circle grows because technologies and automation is increasing in capability disproportionately to, let's assume the tasks remain the same. Keep the car on the road, don't hit anything, whatever. Go land on the moon, don't land on Mars. But what's the impact of that on the functional allocation is where the operators are. That's the human interaction. Are you aware of people looking at that?
I think it's a great question. And now I'm going to get very, very professorial, and I'm going to share my white screen because I want to illustrate for you. Now I can't figure out, come on, give me the white screen. For some reason, I cannot get it to go to a white screen. All right, I don't know why it's not going to give me the white screen. Now I can't even, this thing is, you know, hang on, I'm going to share and then stop sharing. All right, there we go. All right, but let me just, if you can imagine. So I totally agree with what you're saying. I think for me, the bigger issue is not so much are they are all those circles growing at the same time, but rather the difference in the circles between what companies think exists and what really is in the world. So for example, if I were to ask Tesla, okay, so what do you think the size of all those? I agree, let's keep tasks the same. They would tell you that the technology circle is really big and the human circle is really small. That's why they have full self-driving, because full self-driving is the big need of it, right? The reality is that the human operator piece is really big and the technology circle is really small. And there's a gap in there. Like the technology is not actually overlapping the operator, and there's some really bad human interactions in there. So I think that there's, and I've been spending a lot of time on this lately, is what you think you're doing as an engineer doesn't always align with what's actually happening in the real world. And I'm going to get very paternalistic when I'm no longer with the government and start lecturing people on just that. Like, you have a responsibility. You need to remember that you are an engineer who's designing technologies that touch people's lives. And all of you have a responsibility, even if you're not a human in the loop person, to at least avail yourself of the obligation that you have to make technology as safe as possible. And I think a lot of companies, and it's not just Tesla, I think the bulk of the automotive companies who are doing anything with autonomy are not being honest with themselves, save for Ford. I think Ford canceling their recent self-driving program was a really mature move. It's them saying, you know what, we're out. We can't do it. We can't do it at the degree of safety that we would like to do it. So I thought I was very, very impressed by that move.
Yeah, the part that I've been looking at, and obviously part of parcel what you do, is something Karen would have loved to hear you talk, but she's in the air someplace, going somewhere. But the real issue boils down to this thing that we are now getting into pretty heavily, and it's called trustworthiness. So what do you do about trustworthiness of automation, et cetera? And the real thing comes down to, so when people say, oh, the technology circle is growing big, does the trustworthiness in the technological growth and components keep pace with reality? And the answer is no. The answer is no, because those assumptions are all based on, I believe what that sensor tells me. So when you look at your paper and where there were all of those dials and all that sort of stuff, what they wanted, I think subconsciously, you talked to Buzz, so maybe there's an insight to that. Why do you want to have a window? Because that's my backup. I trust my eyeballs.
That's
Not
right.
necessarily true, but I trust my eyeballs.
Right.
So now you want to take my eyeballs and my trustworthy sensor away from me and substitute it with some kind of a gauge. No, you don't like that. I don't like that. I don't think anybody likes that. So I think that the issue of how do these different components, I think the Venn formalism is a nice one to think about, provided you think about it in terms of what the underlying implications are. In other words, as to what remains constant and what changes and what technology actually brings to you. Do you believe an image that your artificial intelligence algorithm says is a human, or do you believe your eyes, which I think can do a better job distinguishing between a deer and a human? We tackled with this one with the current stuff that we're doing in the wilderness search and rescue. We've had that conversation, so you know where I'm coming from. But basically, the issue of what do I believe and what information is useful for me as a human interacting with any system, doesn't matter whether it's space, ground, dirt, whatever. That's really where the focus, I think, should be, is what is the trustworthiness and how should we think about those components, right? And one of the things that you just said, well, no, I don't want to get in a car and take my hands off the wheel. If I take my hands off the wheel, I just removed a sensor. Why should I do that? So anyway, I think that, you're running out of time. There's probably some other questions. Get yourself out here so we can have a glass of wine and dig into some of these issues. It's always fun talking to you about them. But I just wanted to say, in terms of reading the paper, for those who, and I would love to get a copy of the paper.
Okay, I'll send it out.
Yeah, I think that would be, but I wanted to bring that up about the Venn diagram because that's sort of the lead-in thing. And as a lead-in thing, it also encapsulates a lot of assumptions in terms of what the subsequent sections really say and how the design process evolved. So anyway, looking forward to it.
Thanks, Iris.
All right. Do we have time for any more questions, Christy?
We don't have any more questions on board here other than just comments. You know, Rao has been through some surgery with a Da Vinci, so good job, Rao. And then
Still alive.
yes, he's still alive. I think there are robotic surgeries that are okay. There's
Maybe.
lots of
It's just because I think I've got post-traumatic stress disorder I have to tell you, like, when all you do is study how robots can go wrong, it makes you want to move to a desert island.
Yeah, I think you might want to explore your data set and make sure that, I mean, you're intentionally working in the part where it is scary because you need to quantify that.
And the most recent car I bought had no automation in it at all. You even have to roll up the windows.
What? Analog.
Like with any instrument, robotic surgery, this is kind of an interesting one. As at least most of you, and certainly Missy knows, my wife Linda spent many years with surgeons, and she had an interesting discussion with our dean, who is both a PhD and an MD, and with Tung Shen, who is basically Marvel Woman. She does things with eyes.
Eye surgery.
Saved my sight. She is fantastic. And the real question that came up is when it comes to surgery and comes to interaction, there is a big difference between male surgeons and female surgeons. And the robotics that we put into it and the robots that we put in don't reflect the differences between the psychological setting and the sociological setting between a female surgeon and a male surgeon. It's an interesting question that I'm going to pursue with Tung because, like I said, she's my idol, and again, robotically assisted, so it's an issue. How good are the instruments? How do you trustworthy? How much do you trust? Missy doesn't trust that robot to come to her. She trusts the human. Good question. Do you trust a female surgeon more than you trust a male surgeon?
Well, I'm not going to get into the politics of gender on this call. But there is, I am very pro-technology, but I do think that, and this is, like I said, the bigger message that I think we need to walk away, and I'm going to spend the next big wave of my research efforts, are basically, how do you know what is safe enough when it comes to an autonomous technology?
Right.
Awesome. I think that is a wonderful statement for us to end on. It is 1 o'clock now, so we do need to let everybody out to do their next things. Please join me in thanking Missy, and hopefully she'll be here to visit in the not distant future.
Hopefully very soon. Thank you.